Hi, everyone. I'm really excited to be here. This is my first time in Vilnius, my first time in Lithuania, and yeah, I'm super excited to talk in front of all of you. I hope you all had your coffees and your breakfasts and you're ready for a talk about IoT. So in terms of my background, I'm currently a software developer advocate for IoT. I work in the IoT service team for AWS. In terms of my background, I'm a software engineer. I've got a bachelor and a master in engineering, and I've got about 20 years of experience building software for different industry verticals like manufacturing, telecommunications, and also recently some automotive experience as well. I'm a problem solver, so many people have strong preferences towards programming languages or towards architectural patterns and so on. I am the happiest when you give me a problem and I can work backwards to find a solution to that problem. Of course, I have my own opinions about programming languages, don't get me wrong. We can talk about that afterwards. So in this talk, we are going to be focusing on IoT and complexities of device management. So the number of IoT devices is increasing, right? You have them in every domain, in every field. You have devices with different constraints, from really powerful gateways to really small microcontrollers. And all these devices need to be managed. And of course, you can say that the most effective way of managing devices is remote management. However, I would even actually say that it's the only way you can manage IoT devices. So what you cannot do is go to the field to like 1 million different customer homes and plug a USB stick in their IoT device. So that doesn't work. Therefore, because of this proliferation of devices, a lot of standards have come to the rescue, right? So whenever we don't have enough standards, we're just going to introduce a new one. So standards for device management are there. They are actually, increasing in numbers. They are industry specific, and they are there to help remote device management. And still, we have a lot of complexity. First of all, when you're talking about, for example, updating an IoT device over the air, it's clearly not a single operation. It is clearly a set of operations that you need to perform in a distributed manner in order to perform the software update. And of course, this is just one example of a workflow. The most important thing is always integrity. What you don't want to have is a situation where your IoT device is left in an inconsistent state or it is bricked. You also want to have no human interaction, no human intervention. So I don't know if any of you have a Fire TV stick, for example. You plug it in, it's quite seamless, right? I mean, all your settings are transferred to the device. You turn it on, your Wi-Fi settings are also synchronized. So this is, again, another example of a workflow with no human interaction. Of course, we are also talking about complexities of the device itself and challenges of the device itself. So what happens if the device reboots in the middle of a workflow? I mean, this can happen. It can happen for a device in a factory. It can happen for a little microcontroller on a field somewhere, right? So this can definitely happen. Intermittent connectivity also happens, right? So I worked, for example, on an elevator solution whereby when the elevator was going to the ground floor, to the garage, there was intermittent connectivity. So you need to also make sure that your workflow is durable enough to survive through this intermittent connectivity. Battery loss, power cuts, and so on. So a recent example of the consequences of, of the challenges of device management and the challenges of remote management is the situation with Rivian, with their recent software update on the infotainment system, right? So the software update actually bricked the device that was responsible for the infotainment system in the car, and now they're even going so far as to say that hardware changes are needed or that a physical change to the car is needed. And it was really just an issue regarding certificates and putting certificates that were not the latest or the most secure on the device. So this was part of the problem. So it is important to do remote device management. It is important to be efficient and effective doing it. It's important also to ensure integrity. And this is just an example. So what are the goals of this session? What I want you to actually take away from this session is understanding what IoT workflows are, and also the fact that when we call them IoT device workflows, it doesn't mean that the device is the only system involved in an IoT workflow. What are the challenges and what do we expect from a solution to this problem? Also, how can you look at different architectures that can exist to solve this problem and choose the most effective one for your situation? We are going to focus on cloud-managed and orchestrated finite state machines, and then I'm going to give you an example of a firmware update solution that I have implemented, and it's also out there on GitHub. You can have a look at it afterwards, and hopefully we'll have time for a little demo as well. So what I also want you to take away from this session is that you can build solutions in the IoT space that abstract low-level device protocols, right? So it doesn't matter what protocol your device supports. I mean, of course it matters, but it shouldn't be the only thing that matters when you're building an IoT workflow. You need to be able to abstract away from the low-level details of the device management protocol supported by your device. Right, so let us look at some examples and let us go through the characteristics. So this is the device lifecycle, right? So this is the lifecycle of an IoT device from provisioning, onboarding, initial setup, to the device being in operation, going into maintenance and decommissioning. And of course, the device moves through the different phases of the lifecycle. And of course, at every phase in the lifecycle, you actually have different kind of workflows that your device needs to go through. Provisioning, onboarding. I mean, you need to put certificates that are unique. You need to give your device an identity. Then you also need to do an initial setup, hopefully in an automated manner, so that the experience for your consumer, if it's a consumer electronics type of device, is as seamless as possible. Then while the device is in operation, you want to deploy different configuration changes. You also might want to do data collection. I mean, you want to get telematics from your device. You might want to actually provision different services or apps on your device while the device is in operation. The same goes with maintenance mode, right? I mean, maintenance is important. You want to roll out security fixes to your device fleet, and you want to do it really fast. You want to make sure that there are no security breaches, but at the same time, you want to do it in a reliable way so that you don't break your IoT devices. Certificate rotation is also really important, right? So it's best practice to actually rotate your certificates, your device identity, as often as your compliance requirements require it, and also as often as it is sensible, right? Troubleshooting and diagnosis is another case. So we're going to look at an example of a workflow whereby you would enable debugging on your fleet or part of your fleet for just a little while to be able to debug a particular software problem or firmware problem. Decommissioning, again, is an important phase for the device lifecycle. You need to remove all your user data, all your customer data, again, in an automated workflow kind of way, and make that experience seamless. I mean, what you don't want is customers calling you saying, hey, I was trying to reset my device and that didn't work, and you don't want to actually need to interfere. You don't want your customer support to actually be part of that. So what do all these workflows have in common? I mean, they're complex. If you don't like the word complex, you can call it sophisticated. But at the end of the day, it's a bunch of different operations, a bunch of different systems involved. And you also need to be able to trigger this remotely and execute it in a distributed fashion. Human approvals sometimes are needed, sometimes they're not needed, so it depends. And because we're talking about IoT, it is asynchronous and event-driven, right? So in most of the cases, I will not say in all cases, but in most of the cases when you're talking about IoT, you are talking about event-driven communication between your device and your device management platform. Some workflows can be long-running, right? So you might actually want your device to go to sleep and wake up. You might want your device to operate normally until it is time for a certificate to be rotated. So you can imagine having some workflows residing and being orchestrated somewhere whereby your device wakes up at one point of time and this workflow gets triggered. And not just on one device, but on a lot of different devices, like on an entire fleet. The way to deal with this complexity is by simplifying it, of course. So you just decompose it into a set of operations, manage this as a workflow. And here's an example, right? So this is the fault troubleshooting. You want to enable device inspection on, let's say, 10% of your fleet, or basically the percentage of your fleet that has recently experienced a firmware update that doesn't work. So you would just go, you would create the configuration that enables debugging. And this, of course, can be specific to your type of device. And then if the inspection is not enabled, then you would actually enable it. And then afterwards, you start receiving data from your logs, from your metrics, whatever it is. You'd store the data, analyze the data. And after, let's say, 30 days, you would disable this investigation again on the device, everything in a seamless manner, right? So it's pretty much a rollout followed by a rollback of a configuration change. Sounds simple in theory. sometimes it's not that easy to implement with IoT. So again, through the challenges, reliability is important, right? So if you need to interact with third-party systems, you need to respect their SLAs. If you actually are dealing with connectivity that can be intermittent, you need to implement retries, you need to implement the back-off mechanism. Sometimes constrained devices cannot do this. So that's another challenge. Visibility and observability is really important. This is not just about whether one device has performed an upgrade. This is about and devices in different locations, in different regions, different countries, running different versions of the software, or sometimes different major versions, sometimes different minor version. It's about knowing what percentage of your fleet succeeded, what percentage of your fleet failed. If your fleet failed, what are the reasons, what are the top causes? Also, how long does a firmware upgrade take, right? So this is about visibility and observability at workflow execution level across your entire device fleet. Flexibility and expressiveness is another aspect and another factor. What you don't want to have is a situation where you want to introduce a next generation of devices and you need to rebuild your entire device management workflow just because you have a new device and a new protocol. Sure, you need to implement this new protocol for your new device, but you don't have to rebuild everything from scratch, right? So adding new operations to your workflow and also supporting new devices, next generation, should be relatively straightforward in your workflow implementation. And again, complexity, we talk about it again. So here we are dealing with hardware, right? So the complexity of the device itself, different hardware providers, and the interoperability between different hardware, chips, and so on, but also the complexities of distributed systems, right? So decisions around who orchestrates, what component orchestrates your workflow. Is it the device? Is it the cloud? We're going to go into the details of this in a moment. So let's look at design approaches. So here my way of thinking was to split the different design approaches based on two factors. So who owns and drives the workflow, right? So if the workflow is owned and driven by the device, or is the ownership and the orchestration residing elsewhere? And then it's also a matter of the manifestation of the workflow. So a lot of you probably have experience with distributed systems, and you know that sometimes these sort of workflows are not explicit, right? So they are internal to the system and probably documented as a workflow on a wiki page. But when you look at the code, it actually seems like there are multiple microservices potentially talking to each other in a certain way. It's not really traceable that you are actually dealing with a workflow. Even if you read the wiki page with a design document, it will become obvious that, hey, I have a workflow, but it's not obvious in the code, right? So is the workflow embedded? You know, or is it implicit, or is it externalized and explicitly defined? And based on these three design criteria, we have three design approaches, right? So we've got a device-driven way of doing a workflow, and we will look at that. We have an embedded cloud-managed, possibly, or not cloud-managed. I mean, yeah, or an externalized and cloud-managed way of doing things. So the main focus, and this is what you will see in a demo, is on the externalized cloud-managed way of orchestrating workflows. So let's look at the device-driven workflow, right? So this is your FAT IoT device. And your FAT IoT device is basically driving multiple different operations, right? Multiple different steps. Some of them involve interacting with other systems, and some of them are just steps that are performed on the device. And of course, you have a really thin device management layer that performs the remote triggering of your workflow. And the job processing and scheduling, in this case, just schedules job, right? So it's just a normal scheduler. So your device management, so your processor would signal the device management to start the workflow. A workflow would start, the device will do something, and that something is actually a lot in this case because the entire execution is happening on the device. And then the device would also do state tracking, right? So what operation has succeeded, what operation failed. And of course, based on the device management protocol implemented by your device, you can send back information, metrics, logs, and so on. So when does this work? So this works well for less constrained devices, right? So if you have a really powerful edge gateway, you probably can do this. If you have an efficient over-the-air mechanism in place and you can run software updates or firmware updates on your device maybe like 50 times a day without a problem because it's all part of a CI/CD pipeline and it works really well and you've tested it, then it might work. if your device needs to interact with other devices in the network, right, and it's all inside your network and you have control over your network, this might also work. When your hardware changes rarely, it's also maybe a good way to look at it. But of course, this leads to fat edge applications, right? So, your entire logic is going to reside on the device. The flexibility here is not major, right? So if every single time you need to call a third-party system, your device will need to build this. You need to do a firmware upgrade. You probably need to do configuration changes and so on. So rate limiting, SLAs, fault management, retries, all of this will have to be done by your device. So clearly this works well in some cases, but not so well in others. The next way of doing it is, again, this implicit way. So this is a workflow here, but theoretically, practically you actually have multiple microservices, A, B, C, whatever. They all do different things like validation, talking to external systems, and at one point there is some interaction with a device management component or a device management service that actually performs device operations. So it's all really a workflow, but it's hidden in the implementation details of each of the components. This can be easy to implement, based on how large your scale is. It's also maybe a good way to look at things. For small IoT fleets, this actually works. If you know that you're not going to grow in functionality over time and you have a pretty static architecture, this actually can work. Generally, I've seen this being built in combination with device workflows. So in situations where customers I've worked with don't have control over their device because they work with a vendor who actually provides all the device functionality, and they don't have a lot of flexibility in terms of what the device can do. They just have to put up with whatever it is that the spec says, and they cannot change that. So then, then it's a choice to implement this kind of architecture. But you also see that here there is no centralized way to do state management, right? So because of this, if you actually need to build some observability, it's going to be really tricky because all these different systems would have to report their own state. They do it at different times. Then you have to really, do proper crawling through log files to build your state management system. So if you have to do more feature development, it becomes disruptive because then you have to actually do a lot of testing. You have to do a lot of regression testing. Every time you add a new step in your workflow, you literally need to test your entire system. So it's not so easy to make changes. And now let's look at the externalized cloud-managed workflow management and execution. So here, all the components are, in title or in naming the same. But what you actually have is this thin layer of job processing and scheduling, followed by an externalized workflow management. So this is literally a layer of orchestration that happens on top, right? And then you have the multiple steps that are being executed, some of them interacting with the device management logic. So here, you don't really have logic per se. What you have is orchestration of different calls to different systems. One of the systems is device management. In between device management, the device management service or system or component, and your IoT devices, you can have any protocol you can imagine. So if you need to add a new device that speaks a different protocol, you modify this interaction and you modify the device management domain. If you need to add a new step in your workflow, you modify this component and you clearly change maybe the interaction between this and device management. But you definitely don't have to change your entire system. Monitoring is also really easy because the component that does the orchestration also would store state, right? And then if you need to build a monitoring system, you can just build it on top of your state tracker. So you fan out quite well with this architecture. But of course, if you are not leveraging cloud technologies, building this from scratch can be actually quite challenging. And it's often not a good idea. It's also probably quite expensive and quite tedious to build this from scratch. This is the architecture we are going to be moving forward in discussing, in diving deeper into the detail. So now I think that all of you can probably guess how we are going to use state machines and how we're going to map them to that architecture. So first of all, what are state machines? I mean, all engineers have worked with state machines one way or another, right? So they are mathematical models. They are used in computer science. You can control and orchestrate your system behavior over time. And it's used in embedded engineering. It's also used in more, high-level programming. And this is the definition that was taken from Wikipedia. So you probably are aware of it already. So why do we want to use them in this situation? I mean, this is an elegant mechanism to break complexity. You can control inputs and outputs into every state. You can retry at state level, and you don't need to retry your entire workflow just because a state has failed. If you split your logic into a finite number of states with a finite number of transitions and a finite number of actions, then you have modeled the behavior of your system. You can make it event-driven, and this also can help you with loose coupling, right? So with temporal coupling, right? If you have multiple operations that actually are waiting for an event-driven closing, I don't know, workflow mechanism, then if you build it in a state machine manner, other different components in your system can go on. Other different tasks in your system can go on. So this is how the architecture would look like the moment we introduce state machines, right? So you have your orchestrator here, you have your workflow definitions, you can implement multiple workflows or one workflow. The orchestrator would, I don't know, read from your workflow definition, whatever this workflow definition looks like, right? I mean, your workflow definition can be code, it can be XML, I mean, hopefully it's not, it can be JSON, or it can be anything else, right? So this is your state machine definition. The orchestrator picks it up and instantiates executions of your state machines, right? So you can have maybe one execution per device, maybe multiple executions per device based on whatever your needs are. So the orchestrator orchestrates these executions and tracks the state at execution level and at task level. And then here you've got your business logic and interactions with your device management. So now let's look at firmware upgrades, right? When I talk about firmware upgrades, we need to remember there are memory constraints, there are hardware costs. I don't know how familiar you are with the embedded world and how firmware upgrades for embedded devices work, but we are going to assume that the devices support A/B switching, right? So this means that when you put a new firmware image on your device, it will go on a different partition of your device. And then when your device boots up, if it boots successfully into the new partition, it's going to keep the new firmware image and say, hey, I've successfully upgraded. If it fails, it's going to fall back to the old partition with the existing firmware image. So this is the process we're going to talk about. So from a workflow perspective, it's quite simplistic, right? So here you've got an operator, he gets the current version of the device, and then he can send maybe one operation to the device or two operations based on the device management protocol. They can say download and immediately activate the new image, or they can say first download it. If the download is successful, send another activation command and then verify success. From a system view, it's also quite easy, right? Your system receives a firmware upgrade request, validates the information, validates the request firmware information, the device information, validates the permissions, like is this user allowed to do this operation, and then sends the firmware upgrade request, processes the device response and sends the response back. So where do the complexities come from? Well, they come from implementing visibility, making it flexible, making sure that your device does not break, and also making sure that you get enough feedback in your system to be able to act on whatever happened on your device. So if you build this as a state machine, I mean, this is a bit complex. I hope you can see this from the back. So you can split this in a state machine, and this is just one example of a state machine. Of course, based on your use case, you can build it differently. But you can build here 3 separate parallel states, right? Validating the device, validating the permissions, validating metadata of the firmware. These can all happen in parallel, right? Once this has been successful, you can either send the get current version request to understand from your device what is currently running, or maybe this is already happening, right? Maybe you already have this information and you don't need to send another operation. And then you actually send the actual request to upgrade the firmware. You can, if your device supports event-driven responses, maybe, and generally a lot of new device management protocols for next generation devices support this. You can get asynchronous feedback from your device saying, hey, I've transferred the firmware from the server. Hey, I've downloaded, I finished downloading, and hey, I've booted into the new firmware image and I've been successful. You build timeouts for every operation, so you know that your device hasn't responded in whatever you, as an engineer, consider a reasonable time for the device to respond. You just fail that particular state. And you also can interpret the different events and then you either have success of the entire workflow or you have failure of the entire workflow. So this is kind of how it would look like, and we will see this practically implemented with step functions a little later. So let's go into an implementation example, right? So the way I've actually implemented this is with AWS services and AWS components. Of course, this is just one possibility. I have a last slide on open source technologies you can build this with. If you are interested in seeing how that works, let's talk about it later. So this is a fully serverless approach. For the different components, I've mapped them here to technologies so you can have a look at it. So for job processing, I'm using device management. For the core functionality of talking to the device, it's all based on the MQTT broker of IoT Core. And of course, the glue together is done with a Lambda function and the rules engine. The devices, and here this is probably interesting, I'm simulating modem routers. So what I'm simulating is a protocol for device management called TR369. This is a next generation telecommunications protocol. I mean, it's not really important because the whole point here is to abstract away from it, but this is just a real world example of a device management protocol implemented by telecommunications customers for your home routers. So I'm simulating this using Docker. So we will spin up about 100, let's say, simulators running on an EC2 instance, and we will see how we can run a firmware upgrade simulated on all of them. In between the different domains, we have asynchronous messaging using SNS. Yeah, and AWSM is used for deploying infrastructure in a repeatable and automated way. All the code is written in JavaScript, so I'm using the Node.js as runtime environment. So let's have a look at the domains again. So I think these design principles are interesting. Usually when I build a prototype, I like to do it this way because it makes it also easier for me to extend it later. So you see here we have bounded context, right? So every domain is responsible for the logic inside the domain. There are interfaces between all domains. If you need to replace the workflow management, you don't have to rebuild everything. You just replace this component implementation-wise, and you respect the interfaces. Communication is done in an event-driven way. So you've got asynchronous messaging, and of course, the retries and the error handling is encapsulated in each of the different domains. So this is just domain-driven design. So let's see what we're going to see in the demo. Let's look at it, right? So the first thing that's going to happen, remember this job scheduler and orchestrator. So a firmware upgrade request is going to come in, is going to be picked up by an AWS Lambda function that's going to target an IoT thing group. So we're going to group devices into two thing groups. One group is going to be devices on a default firmware version. So that's like a factory firmware version. And then we're going to upgrade them in a simulated manner, of course, to a firmware version 1.2.1 and group them based on the new firmware version as well, right? So once this request comes in, it's going to be an IoT rule that is going to trigger the instantiation of the workflow execution. Now, the workflow is going to be implemented with step functions. So I'm using step functions here to interact with different other services. Amazon DynamoDB is used for storing state while we are waiting for the devices to asynchronously call back. And in terms of messaging, signaling between the different domains, we are using Amazon SNS, right? So when we signal from our workflow that we want to start a firmware upgrade, we're going to pop a message onto an SNS topic, and then the device management is listening to that topic, is going to consume that message, and then it's going to trigger the communication with the IoT devices, right? So this is going to happen over IoT Core, and here we've got MQTT over WebSockets while we publish, and then we wait for the device to send the response. Once the device management parse the response messages, it's going to pop again a message on Amazon SNS, and the workflow management is going to be listening for that and terminating the different states in the state machine with success or failure. So this is how it works on a high level. Of course, we've got, if you remember, we've got from the device management, we're sending operations like to download the software and automatically activate. And then we're going to get an acknowledgement. And we are also, when the device boots up, we are receiving a boot message with the current firmware version of the device, right? So that's going to be the default firmware version. The message is implemented here. If you look at the code, you'll probably see this. They are all protobuf, right? So in between device management and the actual IoT device, we have protobuf over MQTT, and this is because this TR369 device management protocol is actually operating with protobuf and not JSON. This is just an implementation detail. So now we're going to the most exciting part, hopefully, and this is the demo. What I'm going to do is I'm going to start 100 parallel firmware upgrade executions. We're going to look at the state machine, and we are also going to see success, errors, observability, metrics, and so on. So let's see. So what I have is an EC2 instance where I have my entire code, and this is where about 100 Docker containers are going to be starting. So if we look here, you see that we have the code of the IoT workflow management and execution. We will go in here, and the first thing that we need to do is start the devices, right? So once we start the simulators, we are going to be able to see them in the IoT core IoT thing list, right? So at the moment, we shouldn't have any devices if I've cleaned up my account correctly. Let's see. So this is actually empty, but I can show you really briefly the two thing groups that I've created, right? So this is devices on factory firmware version. So when all my 100 devices are going to boot up, they are going to be grouped into this group because they boot up, they send a boot event with their current firmware version. As they get updated successfully, they're going to move to devices on 1.2.3 because this will be the request that I'm sending them to upgrade to. Okay, so let's go back to things. And now I have a little script. So let's see, device agent simulator. So let's look at this script really briefly. I mean, it's a really simple, stupid test script that's looping 100 times and running 100 Docker containers, and each of them is going to contain an agent simulator, right? So again, the simulator connects to IoT core and creates protobuf boot messages, sends a boot event, and then waits for the firmware upgrade request to come in. And then once they receive the request, then they do the operation of actually downloading, send back the acknowledgements, and at the end, we'll send the boot event with a new software version. So let's start this, right? So now we're gonna have to wait a little bit for this 100 devices to actually boot up. In the meantime, we can look and see how many we have started. So again, because we received the boot event, we can see here that the firmware version is the device property. This is the factory firmware version. So the devices boot into this with this version. And as they boot, they automatically get grouped, right? So they get grouped, like I said. This is a form of dynamic grouping. So AWS Device Management supports this sort of dynamic grouping out of the box. So behind this IoT group, there is a dynamic query saying if firmware version is equal to 1.1.2.1, put the devices in this group, right? If we look here, we've got 33 things because all these devices booted up, right? So once we will have all our devices, we can continue and we can trigger the entry point lambda function that I was showing you. So this lambda function is really dumb, so it doesn't do much. All it does is say trigger workflow in simple words, right? So it says trigger workflow, pops a message on an MQTT topic, a rule picks it up and starts the execution of the step function. Let's go to this lambda function. It's called, ironically, create job, right? So what goes into, let me show you the test event. You have to trigger this just once because we are triggering it against the group. We are targeting the group and not each thing individually, right? So if we look at our test event, we're saying here the new firmware version we want to upgrade to. The upgrade trigger, this is just a variable. I mean, of course, you can have an automatically triggered firmware upgrade workflow, whereby when your device comes online, it automatically upgrades. This is not what we're doing here because I'm triggering this function manually, right? And then the target arm is actually the thing group that I was showing you earlier. Let's see how many devices we have now. So if we actually trigger it now, what's going to happen is about 8 or 9 devices will fail. Let's just wait a little bit. Okay, All right, so we've got 100 things. I say it's now time to test our lambda function. Let's go. So again, dumb lambda function doesn't return anything. It popped a message. But what this means is that if we go here now with Docker logs, we will see something happening. This is one device. So it booted up, it is connected. Let's go to our state machine and let's see what's going on in here. Oh, one of them has failed. Interesting. We will look at why this failed. It's probably because we triggered it before the device was fully online. Some of them succeeded. Let's see. So let's wait until everything is pretty much done. Let's see why this one failed. I mean, my suspicion is that we triggered before the device was fully online. And yeah, so get device. You can see here that actually you can, if you click on every state in the state machine, you can actually see the input into the state, the output of the state, which again is an empty array, which means that the thing was not found. So this means that the registration on AWS IoT core side was not fully complete by the time we triggered the state machine. Yeah, so this is why it went, because the device is not found, it went into a publish failure to start. This popped the message onto the SNS topic, and this is how we got the failure of the workflow. Let's go back and see some successful workflow execution example here. How many failures? We still have some that are still running, interestingly. Okay, so I think most of them, up to probably 3, have been successful. Let's just take another random one and check why it has failed. The same reason. So we just went we went a little too fast on triggering. That's okay. I mean, what we can do here to prevent this is implement retries, right? So build a couple of more retries in, and you know, eventually do a nice back off, maybe like a 10-second. Start with a 10 or 20-second back off, and then this will be prevented, right? It's actually in the definition you can do this, right? So let's look at a successful execution, right? Let's take a random successful execution here and see how this looks like. Right, so I mean, is device found? This evaluates whether we found the device. Then we go into whether the device is connected. So connected here means if it is MQTT connected, and whether the firmware upgrade was possible. If everything is okay, then we start the download operation, which means we are sending the actual job document, if you wish, the actual command to the device, and we go into 3 waiting states. We are waiting for the device to say, hey, I've updated the firmware, I've downloaded the firmware successfully, I've transferred the firmware, I've downloaded the firmware, and I've rebooted. So when the device actually sends these messages, what happens is that these wait states get terminated on callback, right? So this is, with step functions, this is called wait for task token, which is happening from Lambda. And then once everything is done successfully and we've interpreted that we have success here, let's see how I can make this a little nicer. Yeah, so once this is done, then we are publishing firmware update success, and this is what happens. So I have not really consciously tried to optimize for duration, but you can see that actually it's pretty fast. But of course, it's also fast because the constraints on the device are hard-coded, right? So I'm giving the device about 20 seconds to say I've succeeded. So this is just the way it's done in the simulator. But it's with modem routers, it's actually pretty accurate, right? So this is how long a modem router would generally take to download the firmware and to swap into the new firmware image if everything is correct. Right, so with this being said, behind the scenes here, I just want to show you one more thing in the state machine, editing the state machine. What you see here is that there is no Lambda. There is absolutely no Lambda function execution in the workflow. This is a little small. Let's see. So, okay. So these are all SDK integrations from the state machine states, right? So it's all happening via a DynamoDB SDK integration with a configuration and API parameters. I mean, this is, of course, for simplicity. If you have 200 tasks, you don't want 200 Lambda functions. You'd prefer to do it as much as possible with SDK integrations. Sometimes you want to have more control than just the out-of-the-box SDK integration provides you. And this is where you would actually go with a Lambda function. Just don't forget that Lambda functions sometimes deal with cold starts. It can be a little slower. Yeah, so from the demo perspective, for now, this is it. I want to show you that the code is really available on GitHub, so you can have a look. You can try this out yourself. You've got a SEM template. You can deploy this in your account and play with it the way that you actually want. Also, the run script, everything, so the code, everything in the code is here. The device simulator, device management functions, job processing, and workflow management. If we go back to the slides real briefly, in terms of conclusion and further work, I mean, what I want you to portray here is that state machines are really helping to break down complexity. Having retries at every level, controlling inputs and outputs is a good way of building robust workflows, including firmware upgrades as well. So how do I see this moving forward? So as you've seen right now, it has one simple device management protocol implemented, right? That's this telco protocol. We could actually use the Matter specification and do this, for example, for the connected home use cases. We could do it for proprietary anything over MQTT, JSON over MQTT, protobuf over MQTT, and so on. We could also explore this for workflows that involve multiple devices in like home automation or robotics. And of course, I mean, this is a prototype, right? This is not production ready by any means, but anyone can take it and build on top of it and so on for whatever use cases. The resources are here. This is the GitHub repository. This is the blog post about it. And this is one of my favorite blogs from Werner Vogels on distributed computing, which I also wanted to share with you if you've got, if you've got interest in distributed computing. Yeah, so thank you very much. This was all from me. And now if you have any questions, maybe we can take one or two questions.
What's the hardware, what's the minimal hardware to be able to carry all of this? How fast enough it?
So, I mean, theoretically, this would work on a modem router, right? So this is an embedded device. To make this work on a microcontroller, you would have to make sure that your state machine is not expecting a lot of interaction with your device, right? So for example, FreeRTOS running microcontrollers, they give feedback on a successful firmware upgrade, but they're not going to tell you if they didn't manage to download the new version or so on. They're not going to tell you more, to give you more feedback. So I would say you would need to tune your state machine and tune your workflow to accommodate a microcontroller. But you don't have to modify any of the higher level part of the solution. You need to modify it to the extent of accommodating your new device management protocol, but you don't have to change, for example, the scheduler. You don't have to change the entire device management or workflow management and execution. So, yeah. Any other questions? Yes?
With regards to the monitoring, you mentioned you would like to get the monitoring also in there with Prometheus or something was on the demo?
Yes. Yeah, so at the moment, and we can go back to that slide real quick. Yeah, so at the moment, there is some basic AWS-driven monitoring, which is dictated by the fact that step functions manage state, right? So you can build CloudWatch Insights. I mean, I didn't show this in the demo, but there is, like, if you go to CloudWatch Insights, there are ways to parse execution states, right? Like how many were successful, how many failed, and so on. But this is all based on AWS technologies, right? So you can integrate tools like Prometheus, Datadog, and even put like Grafana dashboards on top of that. And that should be possible. But you would have to integrate this yourself, so I don't have this in the demo. It's also possible to fully replace step functions by other workflow management solutions, like Temporal, for example. I mean, I really want to experiment with Temporal. I've seen it. I'm actually quite curious about it. I didn't have the time yet to look into it. But it's another mechanism to move more towards the open source world instead of using just AWS services. Right.
Okay, and this is about the state machine monitoring, right? But if you talk about the device monitoring, it will have its own tasks that it will do on the background, not regarding the state machine. How would you get those type of logs into the cloud environment? Because you still want to monitor it from a central location, right? So.
Right. So again, with AWS IoT, you're getting logs about your device state in terms of connectivity, like is your device connected, is your device not connected. When the device disconnects, you also get this sort of messages. You can use device attributes to see different configuration parameters of your device and so on. And this all ends up in CloudWatch, right? So if you use AWS IoT, you'd have this sort of mechanism to do monitoring, and you can also see it in I think it's called IoT Things Hub. It's this new user interface from device management. If you're not using AWS IoT, then whatever other provider you're using probably will give you the basic level of metrics and monitoring. The moment you want more than that, and you want to build more than that, especially for debugging purposes or whatever it is, you would need to ingest your logs separately. I mean, I don't recommend OpenTelemetry here because it's just too verbose for IoT devices. But I mean, you can build your own debug messages over MQTT, for example, and some special topics for that, if what's out of the box is not enough.
Okay, the last part is interesting one. So over MQTT, you would send there the serial logs, for instance. And
I think it depends how much you actually want to send. It depends what you're really trying to monitor. If it is something about certain error conditions or whatever you define at application level, so this goes beyond MQTT level monitoring, beyond runtime environment monitoring, and so on. If you want application level logging, you might consider ingesting over HTTP if it gets to be too much. If you do it over HTTP, you need to open a session every time you're sending it, but it supports higher payloads, right? You could put it straight into S3, for example, if you're using AWS. I mean, I think here it's all about what you're trying to build, right, and how your solution looks like. There are various ways of doing it. Kinesis is another option, right? I mean, you could use streaming if it's a lot of log data.
all right, thank you.
No problem.
I have a question about the concepts. You were basically saying you were doing finite state machines,
Yeah.
but then we saw this diagram and then suddenly we can be running things in parallel. So what is it actually? Because a finite state machine can only be in one state, not running anything in parallel.
Right, but you can have parallel states in a state machine, right? States that execute in parallel.
Well, that's a Petronet then.
Right, but it is a type of state machine, right, that can execute parallel tasks, states in parallel.
Yeah, I mean, you're not calling a finite state machine then.
Okay, I'm going to look into
That's
that.
what- yeah. So basically a finite state machine that can be in multiple states at once, and then you also have joins and everything. That's a Petronet. That's a more complex concept, basically. Also much more powerful. That's why I
Right.
was asking, is like, are we actually doing finite state machines, or can we do?
Okay, so based on my research on finite state machines, you can have parallel states in the finite state machine, and also you can have event-driven terminations of states. But I mean, I'm going to look it up, and we can continue the conversation afterwards, and I can show you my research because actually I've done quite a bit of research in this context because this was there is a research paper behind this that I presented at Embedded World, so I can look at the references and we can talk about it after.
So, but it is actually doing things in parallel.
Yes,
the
right.
thing
So
then.
there are parallel states and there are
Okay,
also
good.
sequential states. But again, I mean, this is based on what you're trying to build, right? So
Yes, yes.
you might have a state machine that doesn't require parallel states, right? Where everything is sequential, right?
Okay, thank you.
No problem.